So I observed others playing Tetris and played Tetris by myself. I found that when we play, we do not even bother ourselves to abstract mathematical models, nor do we care about the variance of the height. I started to think that maybe I should try to describe the evaluate behavior in a less abstract and mathematical way. All I really cared was how the current piece can fit to the board status best. So I changed my view from macro to macro. I started to seek to measure more detailed aspects. From that point, I was able to introduce three more considerations. I considered how well a piece could match the pile surface on the board, how many blocks it could contribute to the pile after eliminating lines, and whether it would create a long hope that would depend largely on the occurrence of I-shapes to be eliminated. With these considerations, I started upgrading my evaluation function. Here is the third idea I had. First, I threw away the calculation of variance of height, since this does not contribute too much but largely includes the computation complexity. Then I introduced three more considerations: roughness of the pile on the board, number of blocks eliminated through eliminating lines, and number of deep holes. The picture on the right is a screenshot of the final program. This slide explains how the roughness is counted. For roughness, I examine the pile after a mock placement and count the change from a block to a blank or from a blank to a block in both horizontal and vertical directions. Roughness can measure how well a piece can fit the pile as well as emphasize more on the holes. So obviously, the fewer the roughness is, the better placement is. Let's go for an example to see how roughness is counted. On the right-hand side, a Z shape is falling. So if we place it here, the roughness will be vertically, there are 15 on the top, and the two holes adding 4 to the roughness in vertical direction. And horizontally will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 21, 22, 23. So totally the roughness is equal to 42 if we place it here. But if we place the Z piece in this position, the roughness will be in vertically, it's still 19, it doesn't change. But in horizontally, it will change to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So the roughness, if we place it here, is equal to 35. As we can see, 35 is smaller than 42. So that means this placement is better than the one on the previous page. And by instinct, we can see that the later one is of course better than the previous one. The next consideration is eliminated blocks. For a piece, we want to add the minimum blocks onto a pile. Thus, in the meanwhile of eliminating lines, the more blocks are eliminated, the better. In this way, the placement that can eliminate most blocks while eliminating lines will be considered the best choice. That's why I introduced this consideration here. Now let's look at a very simple example. On this graph, if the piece is placed here, then we can see that two squares of the piece will be eliminated together with this full line. So in this case, the eliminated blocks equals to 2. The third consideration I introduced here is the length of deep holes. During the observation, if we emphasize too much on the matches and holes, it will be very possible that a deep hole will be created. A perfect fit for that situation is only the I-shaped piece if it is too deep. Thus, it has rather high possibility that it will create a hole or even a long hole. So I want to avoid this kind of situation slightly. However, this is not definitely a very bad situation since it's a perfect fit for the eye shape that could eliminate more lines together. So I did consider it, but did not put too much punishment on that. For example, on the right, it is obvious like in this case, the length of the deep hole is 1, 2, 3. With those three more considerations, the evaluation function is modified to be as shown here. Score equals to line eliminated times blocks eliminated minus average height minus roughness minus holes and minus the length of deep holes. There are some cases, for example, the eye-shaped piece. If 4 blocks can be eliminated, but if it is placed flat, the only one could possibly be eliminated. The algorithm I presented today is not optimal or perfect. There are a lot of improvements that can be done. For example, in this algorithm, all decisions made are greedy and in-time decisions. No one or multiple step look ahead was considered. So it may happen that one decision is the best for the current piece, but makes the next piece very hard to find a reasonable placement. From the previous presentation, one conclusion can be drawn that it is what has been measured that matters, rather than the coefficients. So adding in more considerations that could describe the behavior of the piece may help to improve the performance of the algorithm too. Also, different forms of evaluation functions may also affect the performance, since the evaluation function reflects the different levels of emphasis or rewards on different aspects. So this might also make some difference on performance. Other than those I just mentioned, there are a lot more improvements possible. That's the beauty of NP-hard problem in my view. At last, I want to express my appreciation for all the helps and advices from Fenzhen and Professor Lu. Here's the reference of the presentation. Thanks a lot for watching this presentation.